well, this graph is just fun to look at. But you may notice I have a dy dx here. So a polar graph, right? So it's r is a function of theta. Right? So if that's the case, then you have r's and thetas embedded in an equation. And so how do we get from r's and thetas to x's and y's? All right, there's two ways to handle it. One would be to do a conversion right off the bat. And we talked about this previously, definitely. So if you know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta, basically a parametric equation where the parameter is the angle as opposed to being time. All right, so I can use this information to come up with a dy dx. And you could do it, like I said, one of two ways. Do a conversion early on, change polar into rectangular, and then take the derivative the way you would in Calc 1. Or we can invent some rules right now where we're taking the derivative of these relationships and going from there. So it's just a question of dx d theta or dx dr. The answer is it doesn't matter. All right. So, and the reason I can say that is because essentially I'm going to be taking dy d something here, getting that result, and then dividing it by dx d something in order to get dy dx. All right. So what I would do in this case is take a look at the function that I'm trying to differentiate, or the set of equations that I'm trying to differentiate. And just think about which would be easier to work with. I think clearly the r would be easier to work with. We have a function of two variables, r and theta. So this is an implicit situation. So it's a question of, do I want dr d theta or do I want d theta dr? Right? Either way, it's not going to make a difference. So what we're going to do, is because it doesn't make a difference, is take the derivative with respect to r. And I'll show you what it looks like the other way in a minute. All right. So if I do dx dr, it would be first function. It's implicit. So first times the derivative of the second. The product rule situation. Plus the second function. Oh, sorry. It's implicit. I said it like 3 times. D theta dr. Plus the second function, cosine theta, times the derivative of the first, which would be, well, dr, which is just a 1. All right, so 1. All right. So that's one possibility. Or I could say dx d theta. So I'll do the same process again, just this time with the d theta as my independent variable. So first times the derivative of the second, still the same idea. So r times the derivative of cosine is still negative sine. But it's with respect to theta, so I don't need a dr d theta dr d anything, because it would be d theta, which would go to 1. All right. Plus the second function, which is cosine of theta, times the derivative of the first, which would be dr d theta. All right, so then we're really just kind of taking stock of the situation, saying, all right, well, which do we like more? Right? Which can I make use of more? I can clean it up a smidge. I can clean them both up. I'll tuck a little or in there, because we're not going to need them both. We'll make a choice, and then that'll be our rule of thumb. All right? So it's just a question of which do we like more. Now, do we like? You know, I speak like that sometimes. It's not always a matter of what we like or what we don't like. It's a question of what fits what fits the available information. All right? So what available information? We'll just take a quick look at, sneak a peek at an example here. So first one says, write the equation of a tangent line to r equals 1 plus the sine of theta. So I would ask you, is it going to be easier to find from this equation here d theta dr or dr d theta? If I were to take the derivative of this, what would the left-hand side of it be? Dr d theta, right? Right. So if I needed d theta dr, I could still work with this first equation. I can get a d theta dr. I would have to take the derivative of this and then flip it over. All right. Doable, but it seems like unnecessary extra work. So if that's the case, then we can kind of lock in on this one being our dx d theta. All right. Or at least the preferred one. So why do I go over the other kind? Well, what if you're given a function, a polar equation that's defined as theta equals something in terms of r? If that's the case, you might want to go with the other option. Right? So that's just something to think about. Now, dy d theta. So since we decided to go with dx d theta, there's no point in getting into dy dr. We'll go right to dy d theta. So first times the derivative of the second. So first would be r. The second would be sine theta. So r times cosine theta plus second times the derivative of the first, so sine theta times dr d theta. So this one looks a little cleaner. R cosine theta plus sine theta dr d theta. All right. Now, this is combining the concepts of polar equations and parametric equations. So dy dx is the dy d theta divided by d theta, dx d theta. So we're looking at r cosine theta plus sine theta dr d theta. And then the denominator would be negative r sine theta plus cosine theta dr d theta. And really, there's no simplifying this any further. That's your formula. I believe I'm going to go down this road again. I believe I mentioned at some point that I like to put a derivation on a test. I always put one derivation question where you're expected to invent a formula like we do in class. We did it with arc length for parametrics, and we just did it for the derivative dy dx related to polar equations. All right, so a question on the test could be, and when I'll post up a revised review sheet, but what I usually do is I give you the set of possibilities for a derivation. I'll say it could be this is what the solution would look like, could be that, this is what the solution would look like, and whatever. So I'll give you like three, you prepare for all three of them, and only one of them will be on the test. All right, but it would be something like x equals r cosine theta, y equals r sine theta. What is dy dx? So it's running through this process, but this process even though it seems Calc 3-ish, it's all Calc 1. Right? It's implicit differentiation. All right, so now there's challenges with that because Calc 1 was like a year ago or more in some cases. So, you know, it's like, oh, you should have learned it then. Well, woulda, coulda, shoulda. Like,
got it all probably too.
so the equation of a tangent line. So that's an application of it. Write the equation of tangent line to r equals 1 plus sine theta, where theta is equal to pi over 3. All right, well, personally, I like to get all my busy work out of the way immediately. All right, so I have my formula here. It's got a lot of ingredients, right? But I essentially need dy dx when theta is equal to pi over 3. All right, so dy dx when theta is equal to pi over 3. Now, I can write out that entire formula and then do some substitutions, but before I do that, because I really don't want to do that, I would figure out what r of pi over 3 is, because all of this is happening at pi over 3. So I'd figure out r of pi over 3, because if all I'm going to do is substitute in a 1 plus sine of theta for r, and then replace the theta with a pi over 3, why not just figure out the r of pi over 3 right off the bat? Then I'd figure out the cosine and sine of pi over 3. And then I would need the derivative at pi over 3, dr d theta. So I would make a note, dr d theta is equal, first off, to cosine of theta. But then I would say dr d theta at theta equals pi over 3. And just figure out all these bad boys right off the bat, and then do my plugging and chugging. The notation here, you may not like it. You may feel like it's unnecessary. I did. I'm really just trying to emphasize the notation now so that it's not as shocking when we get to the multivariable stuff. The idea is that when you deal with multivariable calculus, the notation becomes incredibly important. So if you go from never using the right notation to the point where you're so unfamiliar with it that it's like, whoa, what does this mean? When we do it in multivariable all the time, you're going to be completely lost. All right. So all this is telling us, I mean, the vertical line just means such that, or given. So I want dy dx given that theta is equal to pi over 3. So dr d theta given that theta is equal to pi over 3. All right. So if I'm plugging in a pi over 3 for the sine of theta, or for theta in the sine function, unit circle, that's going to be 1 plus sine of pi over 3 is radical 3 over 2. All right, cosine of pi over 3, that's the nice one. That's 1/2. Sine of pi over 3 again is radical 3 over 2. And then, since the derivative of my r equation, my polar equation, was cosine, it's again cosine at pi over 3, which is going to be 1/2. Those are the ingredients for the slope of my tangent line. So I have my formula. R, well, it's not as nice as it could be, but 1 plus root 3 over 2. Cosine theta, 1/2. Plus sine of theta, yeah, sine of theta is next, radical 3 over 2. Times dr d theta, which is 1/2. Denominator negative r. So negative 1 plus root 3 over 2. times the sine of theta, root 3 over 2, plus the cosine of theta, which is a half, and the derivative at pi over 3 would also be 1/2. Right, so all of this stuff together is going to give us a juicy derivative. Just for the sake of sanity, or your own, everybody's, I guess, if you were to carry out some of these calculations, you'd see that the denominators across the board would be 4, right? Because, at least, except for this one here. So if we were to multiply through with a 4, that would clear out all of our denominators. Right? So that would give me 4 plus radical 3 plus another radical 3 over, then we'd have, well, the next one's not quite as nice, negative so negative 4, then minus 3, plus 1. Nice. Just making sure. Just making sure. Because it would be, before we multiply it through with the 4, it would be negative root 3. Oh, root 3 over 2. Okay, yeah, so that first one's got to change. So not nice. So negative 4 root 3. Because prior to multiplying by 4, it would be radical 3. It would be 2 radical 3, right? Radical 3 over 2 times 1 is radical 3 over 2, yes? Mm-hmm. Then multiply that by 4, that would become 2. 2 radical 3, okay. So ideally, I'd like to find any mistakes before I go home and have to do an entire lesson again. Yeah. So 4 plus 2 radical 3 up top. And then negative 2 radical 3 minus 2. This is one of those where I don't even want to check it on the calculator. Because if I do, I'll find out that I made a mistake. And then that'll affect my peace of mind. All the coefficients are even, though, so let's do that. 2 plus radical 3 over negative radical 3 minus 1. Oofa. So now that we've done all that, I'll go back and find the other mistake. Yeah, because 1/2 times the 1 would be 1/2, right? Then times the 4, that would make that a 2. So 2 plus 2 radical 3. 2 plus radical 3. Yeah, it should have been 2 up top. All right, so then negative 1. Do a quick double check-a-rooski of that on the calculator.
It's -1.
It is? Okay.
I plugged it in the original one, and it came out to be -1, so you're good.
All right. So we have our derivative. I mean, it took me a little longer. Bless you. Bless you. They are asking for the equation of the tangent line, though. All right, so that's something that we would have to address. Can't just not do it. All right, so the equation of a tangent line, y equals m times x minus x sub 1 plus y sub 1. Well, we have the m part. The issue that would arise here is that we don't really have anything else, right? So we need an x1 and a y1. So x is equal to r times the cosine of theta. And the r value, the good news is we've already figured that out. This is all happening at pi over 3. So actually, let me note that in there. X sub 1, no, I'm sorry, x sub 1. X such that theta is equal to pi over 3 would be r cosine theta, again, such that theta is pi over 3. So then we're just going to go back, and this is why you don't need to go that far. That's why I do all this stuff on the side here, because I have this information. I know it's a 1 plus root 3 over 2, and I need the cosine, which is 1/2. All right, so 1 plus root 3 over 2. And from that, we would clean it up, ideally using correct mathematics. 1/2 plus root 3 over 4. I guess I don't need this extra equal sign up here. Oh, it's stuck there now. All right. So then r sine theta would be the other part. You need the y value. Pi over 3, can't just change the angle. My angle looked a little big. I'm changing it. Poor quality pi over 3. All right, so this would be 1 plus the square root of 3 over 2 times root 3 over 2, which would be root 3 over 2 plus 3/4. So we have the slope, and we have the 2 points, or we have the coordinate, all right, but in its exact form. So our tangent line be y equals -1 times x minus 1/2 plus root 3 over 4 plus root 3 over 2 plus 3/4. All right, so that ends up being the equation of our tangent line. And it's not pretty, but it's exact, and exact is what we need. Okay, so. Well, I mean, we would prefer pretty and exact, but this is the best that we can do when not dealing with overly simplistic cases. Right? That's the thing with polar equations, is that if I make them too simple, then it starts questioning the need for the calculus to begin with. If I were to give you a circle and then tell you find locations where there's horizontal and vertical tangents, you don't need calculus for that. You just need a ruler and eyes. Right? But when you get into like a limacon, the calculations can get a little crazy, but the best you can do by eyeballing it is like, well, I think there's one there, but you wouldn't even be able to come up with a reasonable estimation of what that, what the location would be, all right, without doing the calculus. So it really is, for this particular concept, I'd say it's feast or famine, because it goes from like, this is so easy to the point where I don't need calculus to, all right, the cases where we do need calculus, this is a nightmare. Don't they have like a middle of the road type of example? And the answer to that is, no, not really. And so how do we handle that? Well, I give you an omit on the test. That's how we handle that. All right, so, but you know, you look at a problem like this, and you're like, wait, so is this an easy one or is this a hard one? I would say that this is it's just one. You know, like, I mean, look at, it's a simple-ish polar equation, 1 plus sine of theta. That's not an outrageous equation to work with. But then look what that led to. There's kind of like an exponential relationship between the type of equation and the amount of work that you need to show in order to get the answer. Right? So, and also depending on what you need to do with it. The good news is for number 2, which is the one I'm going to leave for you to try on your own, like a lot of the work is already kind of handled, like derivatives and things like that. So that's going to be a fun problem for you to work on. But yeah, it's one of those like, I was planning on omitting one of those derivations. No. Derivations, you know what the problems are going to be in advance. You don't want to omit those. Those are your gimmies.
Same points.
Yeah. It's the one where, like, personally, I've seen problems on tests, and I sometimes put them on my own on purpose, where it's like any student would look at it and be like, I know how to do this. I also know it's going to take me the next 45 minutes to do it. With that in mind, that is my strategic omit, because I don't want to spend 45 minutes on a problem that I know how to do. Right? I save it, you know, I save my omits for that type of question. The thought-provoking questions, those are the ones that once you do the thinking, you can usually crank it out pretty quickly. But something along these lines, it takes a little while to do. So save it for the end and just write OMIT on it. And just for clarification purposes, because it has come up in the past, that not everybody knows what omit means. And this is not meant to sound like a snot rag or anything like that.
All right.
It's a question
horizontal
that you're allowed to
tangents,
skip
if you're just
and still
talking
get
about
credit
an
for
ordinary
on a test. I don't know if that's actually the
graph or
definition
some
for it,
kind
but
of
that's how I define
function-y
it.
sort of
So
thing.
you can skip over it, but then I give you credit. This is the part where I'm cool. So I give you the credit. So if it's a 5-point question, I give you those 5 points.
Turns around.
So as opposed, and the only reason I ever started doing that is because I didn't like answering the question, hey, can we do the omit for like extra credit? I'm like, no, I gave you the omit so I have less to grade. That's why I did it. If you start doing it, then I have more to grade. That's defeating the purpose. So you get the points. You have the free 5 points for that question.
And then it goes
Right,
up,
so
goes
it's
over
a
the
nice
edge,
little.
and then it bows you back inward, and then shoots you down, and then like ruins your life for a little while, and then it lets you off. So, but it's great. It's great fun. And actually, I gotta say, it doesn't look too much different from this. Actually, it's steeper. It's straight up on this side. All right, and then there's a little loop-de-loop, so there wouldn't be a cusp. But it's a good ride. I enjoy it. Yeah, that's all I have to say about it. It's relaxing on the way up because you're completely horizontal. Okay? So it feels nice. Then, you know, on the way down, it's terrifying, of course. But worth it, you know, because what happens is when you're a younger person, you have like all the courage that goes along with being younger. Then you get older and you realize things like death can happen. And then you have kids, or in my case, kid, and they want to do all the stuff that you were able to do when you were younger, the exciting things, but you can't let them do it by themselves because of that death thing I was talking about before. And so you do it with them, pretending the whole time that, nah, this is no big deal. I'm not scared at all. But eventually your 8-year-old or 9-year-old will turn up to you one day, look at you right in the eye and say, you're scared to death, aren't you? At which point you say, yes, I am. Was that?
You ever been a big cop in Six Flags?
No.
You should go.
It's one of those.
Yeah.
I have a feeling I will be sampling that at some point because
I was fine with Sesame Place, like a little Legoland action. We were good. Like, all right, we're going up, but I'm not scared too much. And then we graduated to Disney, and Tower of Terror threw me for a loop. But then they rebranded it, at least the one in Disneyland, as the Guardians of the Galaxy ride. So they had the nice music going on, so like it took a little of the terror away. But now he's getting to the point where he's like, enough of this. Splash Mountain has its place in my life, but yeah, what's the story with that Batman ride? What's the story with that, like anything that was like death-defying nonsense? So, of course, yeah. I'm hoping to get like lights and stuff because the math isn't getting it done. So I'm hoping like the asides might do something, but never. One good video that I made last week was when we had an early dismissal at the high school. Apparently I reacted, and it ended up on the video. So it's a worthwhile look. I'll point out what video it was. Words to the effect of, yeah, baby! Like at the top of my lungs. So anyway, on to the question. Points where there's a horizontal, vertical, or otherwise some other funny business going on. So we need the derivative. Fortunately, we have the derivative, kind of. We have the ingredients for the derivative at a particular point. We have a technique by which we can compute the derivative. The issue here is we need to solve for values rather than be in a situation where you're given the values. So unfortunately, it's kind of a back-to-go kind of situation, but you can refer to the graph, and that's definitely helpful. All right, so it goes back to this idea. If you're just reflecting on the original derivation, it's a question of, do I want to work with this, or do I want to start from scratch? And it's not really scratch. It's more so, do I want to do a conversion on my original function, r equals 1 plus the sine of theta, and convert that over into rectangular form, and then go from there. The drawback to going to rectangular form is that it's going to be completely in terms of x's and y's. So you can get x values and y values, but then eventually you'll need some thetas, all right? Because if we're looking for the parameter, in this case theta, representing where it has a horizontal or vertical tangent or a cusp, we would need to figure that out. So if you kick over to rectangular form, you could accomplish that. You just have to do a little bit more work down the line. Not terrible, but sometimes a little bit more than you want or have in mind. The other issue that comes into play is sometimes when you go into rectangular form, the function is so unrecognizable because it's not your classic parabola, polynomial function kind of thing, or a conic section. You haven't really seen what a limacon looks like in rectangular form. It's not pretty. So then if you were to kick over into rectangular form, you would then have to take the derivative of that thing. Maybe that's not something you want to do. All right. So all of that is a preamble to say, well, I'm just going to use the formula that we came up with because I sold myself on that. All right. So I need a dr d theta which is cosine theta. All right. So then I need a dy dx and again, we're just referencing the formula. I'll just try to get it on the same screen so you can see it. All right, so we're taking the derivative of 1 plus sine theta, which is cosine theta, and then popping it into this everywhere we have a dr d theta, which isn't terrible because everything else is going to stay put. All right, let me see if I have enough wiggle room. I think I do. All right, so r cosine theta plus sine theta times cosine theta, all right, over negative r sine theta plus cosine theta, so I'm just going to write cosine squared. nib is taking a beating. Oh, it's not a double-sided. I'll grab my backup stylus. All right, so this is what we're working with. From here, I can start getting into things like horizontal, vertical tangents, and cusps. All right. We're also going to make use of the graph. Some advantages to that would be, well, I think it's an obvious advantage. If you see a horizontal, vertical tangent, or a cusp, like let's say, for example, you don't see a cusp, then I'm not going to look for that analytically. If I see two horizontal tangents, I'm expecting to find two answers where the derivative would be equal to 0.
Why are we not substituting R in?
R I was going to do in the next step. Yeah. So if there's any cleaning that you could do at this point, that's what you'd be looking to do. So look for identities. Sometimes they pop out. You know, I have a cosine squared. I'll be on the lookout for a sine squared because they'll combine to equal a 1. You know, a nice Pythagorean identity. So let's pop in the 1 plus sine theta times the cosine theta plus sine theta cosine theta. Clean that up in a sec. Negative 1 plus sine theta times sine of theta plus cosine squared theta. So cosine theta, I'm just going to distribute. Cosine theta plus sine theta cosine theta plus the sine theta cosine theta that's already there. Some nice like terms that we can combine. All right, and so on the bottom we're looking at negative sine theta, and that would be minus sine squared theta plus cosine squared theta. All right, still looking for identities, if possible. But at this point, it's just algebra. You know, nothing too crazy, a couple substitutions. All right, we're looking at cosine theta plus 2 of those sine theta cosine thetas and then we would have negative sine theta. On the bottom, I'm just going to leave it as is. So that's what my dy dx is going to be.
Do you not have the bottom being negative sine theta minus 1?
Well, because this is a negative sine squared theta, it wouldn't actually be the identity, so unfortunately. Now, these two we could put together and actually get the double angle cosine identity. On the top, we have a double angle sine identity. It's just, it doesn't seem like it's going to really do anything for us. All right, so what do we do now? Well, going all the way back to Calc 1, we know that we can do two things once we find a derivative in order to find critical values. You can take your derivative, dy dx, and set it equal to 0, or you could set it equal to 1 over 0. All right? So basically figure out what would make it equal to 0, figure out what would make it equal to undefined. Because essentially, dy dx is slope. This base component is talking about slope. Slope of a line tangent to a curve, whatever. You make it fancy if you want. But it's slope. When slope is equal to 0, it's a horizontal line. When slope is undefined, it can be a vertical line. The drawback to this one, though, this is where we have to do our work. We got to flesh it out a little bit. There's a lot of things that can make a fraction undefined having nothing to do with the slope. Maybe the function is just undefined because there's an asymptote in there or something. Right? So that we'll have to flesh out. But on the top, If we just figure out what makes that equal to 0, we should be able to identify some horizontal tangents, if they exist. And we'll use our graphs to support our work here. All right, so I'm just setting the top equal to 0, because if I were to take the entire fraction, set it equal to 0, then cross multiply, bottom's canceling out anyway. All right, that's, again, Calc 1. It's one of the first shortcuts that even if your teacher doesn't show it to you, you figure that one out on your own. Like, wait a minute, why am I setting a whole fraction equal to 0 when the bottom's just going to cancel out anyway? Can I just set the top equal to 0? Absolutely. All right, common factor of cosine theta. So 1 plus 2 times the sine of theta equals 0. It's nice when I tell my Algebra 1 students that the concept of the greatest common factor will never go away. You're going to be dealing with that for the rest of your mathematical lives. And then that very evening in Calc 3, here we are, greatest common factor. And you can say, definitely, it never went away, right? Greatest common factor never goes away. Take each of your factors, set it equal to 0. It's a quadratic situation. All right, cosine theta equals 0 is good to go. We'll take care of that in a sec. But let's refine the 1 plus 2 sine theta. That's going to be sine theta is equal to negative 1/2. Man, this unit circle thing keeps coming up over and over again. It's like it's important or something. All right, so in terms of, we'll just keep it to 0 to 2 pi for now. Actually, I should read the problem. No, it didn't say domain. Okay. We'll keep it from 0 to 2 pi for now, and then we'll branch out as needed. Because sometimes it's an infinite relationship, and you have to account for many turns around a unit circle. But if we're just living in the 0 to 2 pi domain, where is cosine equal to 0? What angle?
Pi halves.
Pi halves, and what's the other one? 3 pi over 2. All right, we're just getting a set of possibilities here because, again, nice guy letting you use the calculator, right? So in a few minutes, we'll be able to flesh out which one of these are the ones that we want to keep. I'm not going to make you use limits to verify any of this stuff, all right? Fun fact, if you're really going to truly do it analytically, you need to use limits to verify. Not going to happen, so you don't have to worry about that, all right? Before I even said that, you weren't worried about it. But I needed you to be worried about it so that I can say that I'm going to make you not be worried about it. It's a way of, like, elevating myself in your eyes. So anyway, where is sine equal to negative 1/2?
Sine of 5 pi over 4. I'm sorry, 5 pi over 4.
5 pi over 4?
Oh, no, I'm thinking square root of 2. 11 pi over 6.
11 pi over 6 is one of them. Now, if it were 5 pi over 6, that would give you a 1/2. So it's one that's really close to that. It's another pi over 6.
7 pi over 6.
7 pi over 6.
Not all. 7
You know what's funny? My first year teaching, I got in trouble for that.
Really?
Yeah, they're like, we heard from a parent that you and I'm like, really? You gotta be kidding me! That was a joke. You know, so.
Where were you teaching at the time?
John Jay.
What grade?
Oh, what grade? 12th grade.
12th grade seniors, really?
Yeah. I'm like, man, you'll find anything to complain
Probably
about.
all credit more than you.
Exactly.
I like the derivative of tan x. Secant x tan x. Derivative of sex is sex tan x.
See, like you don't even need me to come up with this stuff. You got better stuff than I have. Like, all students take cash. There you go. I had to settle on the very PC version of it. All students take classes. Yeah, that's what everybody corrects me with. But is that true?
Not all students.
Not all, but and actually, not all students take classes either. But yeah, yeah, they pay for it. They don't always show up, but you know, it's part of the fun, I guess. All right, so we have a set of possibilities here related to the horizontal tangent. Now let's see if we can come up with a set of possibilities that would address the vertical tangent and or cusp. All right, if there's going to be a cusp or a vertical tangent, it's going to come from this set. All right, so that's the big concern here, is that what we get here for a set of solutions, it could go either way.
Can we just turn sine squared and cosine squared into one, or we lose solution?
See, that's
Yeah, but you can just it's negative one. Check out.
that would be negative sine squared minus cosine squared.
No, we're just taking the negative one.
Oh yeah, we'll just change math. It's cool. Why not? Why not? Make them up as we go along. I mean, listen, I've been doing that for years, so it's perfectly fine. Yeah, got this far. I'm going to change the order a little bit. I just want to emphasize this because this pair of values is not the Pythagorean identity. What it is, though, is a double angle identity for cosine. So there's two avenues you can take from here. One would involve you knowing your double angle cosine identities. All right. The other would be a simple substitution, which I think is probably more universally accepted. Cosine squared theta is 1 minus sine squared theta. A little offshoot of the Pythagorean identity. You know, the cosine squared theta plus sine squared theta is equal to 1. If you solve it for cosine squared theta, you get this. So it's an effective substitution because I've now transitioned from an equation that has multiple trig functions in it to something that only has one. All right, so negative sine theta plus 1. These two are going to combine to give me a negative 2 sine squared theta. You could save yourself a step in this one problem. I guess I'm kind of undercutting my motivational approach here. But you could save yourself a step if you know the three variations of the double angle identity for cosine. Because one of them is 1 minus 2 sine squared theta. The other is 2 cosine squared theta minus 1. All right, if you happen to know those, then you can make that substitution very quickly. All right. Full disclosure, those are not things that I really truly knew until I became a teacher, and I had to know them. And I knew the Pythagorean identity. I knew one of the cosine double angle identities, and I always just built up the other ones as I needed, basically doing this. All right. So it's quadratic, so clean it up. Activating a pen, of course. 2 sine squared theta plus sine theta minus 1 equals 0. Just flipping the signs, changing some things around. Another concept I just got through telling my Algebra 1.
Just times over -1, right?
Yeah, and just juxtapose some things. I wanted in descending order. Yeah, factoring trinomials, never going away. Assuming, of course, it's factorable. All right. So we give it a look. If not, maybe we complete the square. So we would need a positive 2 and a negative 1 to get us where we need to go, right? 2 sine theta minus sine theta gives us a sine theta. All right, so we'll get 2 solutions, really. Sine theta, or 2 equations that'll help us get solutions. Sine of theta is equal to 1/2. If you set that first one equal to 0. The other would be that sine of theta is equal to -1. All right, so just thinking in terms of a single rotation around the unit circle, where is sine of theta equal to 1/2?
5/6.
9/6. What's the other one?
5/6.
Mm-hmm. Very good.
Other one's pi.
Close. It's definitely on an axis.
It's
That's where cosine's equal to -1.
it's be three
pi. Yeah,
3 pi over 2.
3 pi over 2. Okay, so we have all of this stuff. Look at this. Look at this non-calculus stuff. All this stuff that made the problem challenging.
What's the unit circle?
Shouldn't you have?
It's all unit
What's
circle
all the
stuff.
unit circle?
Shouldn't you have your positive and negative reversed because you want to
You know,
sum to a
remember?
-1, so you want a
Sine
-2,
zero,
positive 1
1,
instead of a
0, negative 1,
positive 2,
yeah, 0,
negative
and
1.
then cosine is 1, 0, negative 1, 0,
Am I crazy? Am I it's not
Again,
multiplying
it's-
right?
You talking about from here to here?
So
Square root of 3 divided by 2.
I get 2 sine theta,
Square root
negative
of 2
sine
divided
theta.
by 2, square root
Give me
of 2,
sine
then
theta.
1/2 divided by square root of 2 divided by 2.
So we do have some overlap between the two sets. And this is where the calculator becomes our best friend, because you'll notice that we have a 3 pi over 2 in both sets. So that 3 pi over 2 is our wild card. That could be a horizontal tangent, it could be a vertical tangent, or it could be a cusp. Or maybe it's nothing at all.
I'm just confused how you got from sine squared theta to 2 sine theta minus 1.
From sine.
I mean 2 sine squared theta to 2 sine theta minus 1.
No, it's 2 times squared.
They factored out? Yeah, we factored it.
So from here to here?
Yeah.
Yeah, I factored it out. I just kind of pretended that it was 2x squared plus x minus 1 and just factored it old school like a trinomial. Just signs instead of x's. Worst case scenario, again, pretend that they're x's instead of signs, pop it into the quadratic formula, get some solutions, and then instead of it being x equals, make it sine equals, sine of theta equals. All right? Because you shouldn't really get bogged down with the algebra. Right? Now, that being said, if some of the values are funky, because I mean these are unit circle numbers for sure, but if they're some of the funkier ones, like radical 3 over 3, if it were a tangent function, that could be a problem. All right, you might not be able to recognize those. So anyway, we have to flesh out what's what. So that's where we go to the calculator. All right, so when I hit enter after typing in pi over 2, it places me right at the top of the limacon. Limacon? Well, limacon or cardioid, one or the other, it doesn't really matter. I never get them straight. The weird one where they both have the little divot without the loop, I sometimes get those confused. All right, but anyway, we have a horizontal tangent, definitely at pi over 2. All right, maybe more, but we'll start with the pi over 2. All right, how do I know that? I plotted pi over 2, the theta value of pi over 2. It put me right there. All right, if you need the coordinates, you can just jot those down. They give you x values and y values. 0, 2, x and y. This will all be up on the recording. The iffy one is the 3 pi over 2. So 3, you just start typing 3 pi over 2. You don't have to go back into value because it's still activated. See where that puts you. Origin, which is right at the tip of that cusp. All right, so we've now identified the location of the cusp. That happens at 3 pi over 2, specifically the origin, if we're in rectangular coordinates. So you might look at this and say, oh, this is really tedious. It's better than the alternative. So 7 pi over 6, horizontal tangent. corresponds with, I'll just say about negative 0.4 ish, if you want, negative 0.25. All right. It's a pretty safe bet that once we figure out what angle gives us this guy, we'll have all of our horizontal tangents. So, strong suspicion that that's 11 pi over 6. Mainly because that's the only one left. All right, so 11 pi over 6. And that gives us the positive counterpart to that last one. So 0.4 comma negative 0.25. And again, it's approximate 0.4, but yeah, it is what it is. All right, so then we've accounted for all of our horizontal tangent possibilities. The only things that are left are our vertical tangents. Now, based on the picture, we have vertical tangents. We can see them. And they're going to happen at pi over 6 and 5 pi over 6. All right, but we can verify. So pi over 6 gives us a coordinate of about 1.3 comma 0.75. And the other one is symmetric to that, so we could assume it's negative 1.3. You don't want to take the chance during a test, I respect that. So type it in anyway. 5 pi over 6. What's it going to hurt? All right, negative 1.3, approximately, and 0.75. All right, so we fleshed it out. We needed those values because, I mean, what would I type in order to verify the location? I mean, I'm not just going to hit trace and scroll around and hope that it's close to something that's recognizable. Sometimes that happens. I mean, if this were a question that said, identify the location of a cusp, wow, this is great. There it is, 0, 0. Show all steps necessary to justify that using an analytic approach. Yeah, okay, well that sucks. But you would at least be able to pick it off the graph. The other ones, I don't know. I mean, you could ballpark in some cases. I mean, the horizontal tangent at the top, you'd probably be good with that too. Assuming that, and it is the case, but the scale here is that this tick mark is 1. Pretty solid assumption that that's 2 units up, even if the graph didn't tell us that. But, you know, not always going to be the case. Ninja mode. There we go. All right, so we have all of our information here. And I only just jotted down the coordinates in the event that the question asks you to find the equation of a tangent line, in which case you need the coordinates, or maybe just simply ask you for the coordinates, the x and y values of the Cartesian coordinates, the rectangular coordinates. All right, so obviously there's a lot of teeth to a question like this. Pretty exciting. All right, so but it's good if you don't have any experience with vectors. This is good because I teach it from the ground up. All right. If you have a lot of experience with vectors, well, it's good and bad. It's good because we do it a little bit differently than you might have done it in linear algebra or even like an engineering course. But there's enough similarity where you're going to be like, I know this already, I know this already, I know this already. But you just got to stay with me because you'll get to a point where you don't know this already and you'll need to kind of flesh it out. The difference between linear algebra and vectors in this course is it starts off immediately. It's the notation, right? Instead of using the square brackets and vertically orienting our vector, we use these triangular brackets, although it doesn't look very triangular here, right? So right off the bat, it's a significantly different way of thinking, although the operations are going to be very similar. All right, so let's talk about what a vector would look like, or at least initially. So sketch a vector in a plane from initial point P11, right? So just plotting points. to 4, 5. So 1, 1 to 4, 5. So rough sketch. So here's 1, 1. Call that point P. 2, 3, 4. And then 2, 3, 4, 5. All right. It probably could have made more use of my available space here, or more effective use of it. But I didn't, and so here we are. All right, so I still have a line draw tool that has not changed. The only thing that changes is my ability to actually use it. All right, so this is a vector in space. Vector in space. It's a variation on a movie quote that really can't say in class, although it's fun. I think I heard. So what we have here is a directional relationship. It's always from one point to another. What we want to do is anchor the starting point of our vector at the origin. All right, so that's really what's going to end up happening, is at any 2 points, we're going to have vectors that, or a vector that symbolizes the direction from one, and magnitude from one point to the other, but we want to anchor it at the origin. All right, so this would pop down to 0, 0. So my P prime, I'll call that P prime, because any transform point, the image we denote with a prime symbol, which is just my way of trying to make this as confusing as possible, because as you know, prime also means derivative. But unfortunately, and I'm just kidding about trying to make it confusing, unfortunately, the prime is used for both derivatives and also images in a transformation. Right? It's just an unfortunate decision that somebody made.
You could just do the zero vector.
What's that?
You could just do the zero vector.
I could, but I wanted to show that that was where P was going. So I moved the point P down 1 and to the left 1, so I'll do the same thing with Q. So down 1 and left 1, so I'm just going to put it roughly around here, so that's my Q prime. And it's supposed to be parallel, so I already screwed that up. We're getting to the point where you might just have to believe me about that.
Wait, if you move Q down 1, 1, should I just move a line?
Yeah, so it's still on the same line. You have the Q at 4.
Oh, did I just... Oh, I threw myself off with my own inability to draw.
The freehand graph.
The freehand graph strikes again. For the first time. No, actually ever. Always. Well, I do appreciate you not letting me attempt that 37 more times before letting me know. That's always a good thing. All right, so the vector that's anchored at the origin is defined by the endpoint. All right, and that endpoint, if we dial it back, originally it was 4, 5. Dial it back 1, or down 1 and back 1. Instead of 4, 5, it'll be 3, 4. So then that becomes, in vector notation, the triangular brackets 3, 4. All right. The benefit of writing it like this, it might seem not necessarily the most useful thing in the world, but hopefully it's obvious that we just went from defining the vector by 2 endpoints to defining it by a single endpoint. If we know that one of them is the origin, or the zero vector in this case, then
you have a way of defining the direction and then ultimately the magnitude when we get to that of the vector just by knowing the endpoint. All right. So if it's anchored at the origin, all that works out. All right. So a vector in general is really just a line segment indicating the magnitude and direction of something, maybe in motion, or a force applied to a particular object. All right, so magnitude and direction is really the key words there. All right, so let me just throw a little underline on those bad boys. A little highlighter action. Okay, it looks like I scribbled it all out, but whatever. All right. The vector with initial point 0, 0, terminal point x, y can be written in component form. What I can see on my iPad and what you can see is always going to be an issue for me, as x comma y. All right, so we're looking at the component form of the vector. The x and y values of that vector are known as the scalars. All right, so anything that represents a linear distance is going to be a scalar. All right, so if you're given 2 points, you can come up with the vector in component form without doing all this stuff. Really all we're doing is finding the difference between the corresponding x values and the difference between the corresponding y values. So vector v, in this case, would be 1 minus negative 2 and 2 minus negative 2. So 1 plus 2 is 3. 2 plus 2 is 4. All right. Order matters because order of subtraction will define direction, right? So it's terminal minus whatever your initial is, all right? Because if you did it the other way around, it would still be anchored at the origin, but it would be pointing in the wrong direction, right? So very important that it's terminal minus the initial. But that's pretty common for just about everything that you do. It's usually the initial being subtracted from something later on down the line, VF minus VO, or VI, depending on what textbook you're looking at. So that part should be easy enough. Vectors are equivalent if they have the same magnitude and direction. Right? So I can draw a bunch of different vectors in space that in such a way that when I pin them down, they all give me the same vector in component form. Right? Here's an example right off the bat, because I started off in that intro example with 1, 1, and 4, 5, and that gave me a vector 3, 4. But then I used negative 2, and 1, 2, which would be something like here. I'd have a point down in the negative quadrant here, and then 1, 2 would be somewhere over here. When I put it in component form, it would still give me 3, 4. Right? So it's the same vector. It's just maybe earlier in a process. It's kind of hard to really understand until you have some context associated with it. But there are plenty of ways in which vectors can be the same. If you define the downward force on an object as a vector, okay, so are you telling me that there's only one way that you can apply a downward force of, let's say, 50 pounds? So there's only one human that can weigh 50 pounds, right? So no, that's not how it works. There's plenty of things that could weigh 50 pounds, right? So that's the idea there. Some properties of vectors. I think some of them are obvious. For addition and subtraction, you're talking about just adding the corresponding components. So, we're denoting here with a sub 1, a sub 2 to represent vector A, b sub 1, b sub 2 to represent vector B. You're just adding the x values of each vector together and then the y values of each vector. Subtraction works the same way. Scalar multiplication, that's a dilation if you're thinking in terms of transformations. Right? So if you double the coordinates, you're going to double its distance away from the origin. Right? and that'll have impact on the distance overall mathematically. All right? But there are some other properties that aren't necessarily obvious. But one of the cool applications of scalar multiplication, vector addition. Huh, look at that. Almost skipped over an example. So this is just practicing the operations, but I think that's something that you can handle, so I'm going to put a little star on that. The cool application of vector addition is that it can take the place of, if you remember the law of cosines, maybe it's something that you prefer to forget. It's good news, because you don't have to use it. Vector addition allows you to do what the law of cosines would do in terms of finding sides and angles in a parallelogram without using the law of cosines. All right, so that's a little added bonus there. But if you like the law of cosines, that might be a problem. All right, so vector addition graphically, very simple. And I don't say that about a lot of things, so I'm going to trace over that line. Now, there's part of this where you're going to say simple for you. And that's only because I have the technology. Okay, maybe I don't. This one I'm going to have to freehand. Oh, it's kind of already freehand, but I'll just get a better one. All right. So, undo. I need my little hand icon here. Yeah, there we go. I'm going to do a little bit of that. And then a little bit of that. Yeah, again, like I said, easy for me to say. All you're doing is creating congruent opposite sides. So if I had a straight edge, if I were doing this on paper, I haven't written on paper in ages. I don't like paper anymore. All you're doing is just matching up the length of the side. So if you have the edge of a piece of paper, just make a little tick mark to represent the length of the side, and then slide over, maintaining the parallel relationship until you get to the other side, and then just mark off that distance. And then do the same thing. I don't have a folder long enough, but do the same thing. I could zoom in, I guess. On this side, get the whole distance. Maybe I will. Get the whole distance. Get the whole distance. And then swing it on up here and create your parallelogram that way. Most people are fine just doing a rough estimate. Your question would be, am I fine with that also? If you do it on the test, of course. I don't need a work of art. I'm not a hypocrite. Protractors, compasses.
By the time you finish, the test is over.
Yeah, exactly. Like you've done like the one problem.
Omit the rest of the test.
Oh yeah. It's like a disaster. You know, I'm not even going to bother with the line draw tool on this one because it's just shot. It's trying to like fit me in a particular slot here and it's not working out well. All right, so like that, essentially, without the shaky line drawn. All right, so that is U plus V. Now, if I need the actual component form of that vector, I need this coordinate over here. All right, well, let's kind of wrangle out that information. So drop an altitude here. Vector U has components 2 and 3, which means it's a horizontal movement of 2 and a vertical movement of 3 to get you from the origin to that location. So 2 and 3. So I can do the same exact movement from the end of vector v, which is at 4, 1. So I'll just mark up this part of it also. That's not going to look nice. I'm going to go orange. I know it's shocking. So this is 4 and 1. All right, so all I need to do is from point B, which is the end of vector v, I know I covered it up, I'm going to go an additional 2 units in the x direction and 3 units in the y direction. All right, so we're looking at and so that would make this coordinate up here. And so I'm just looking at the coordinates, not the vector itself, the component form, which, I mean, they're going to go hand in hand, but if I started off 4 and I'm going an additional 2, I'm now at 6. If I started up 1 and went an additional 3, I'm now at 4. All right, so that's our graphical representation leading us to the vector 6, 4. When I show you how to find magnitudes, then you'll see that really it's just Pythagorean theorem all over the place, because the magnitude formula is how you'd find your distances.
Professor,
Hmm.
were you cutting the x values in half for a reason?
Did we cut the x values in half? I cut the x values in half.
I'm looking at the graph, and they're all marked, like each one.
According to the graph, it's
Oh,
on
it's
the
moving
scale.
by like a half point now.
Oh yeah, I couldn't figure out how to
Scale.
set up the scale on GeoGebra to make it look the way I wanted to, but yeah, they went by half units.
Oh, they did. Huh?
Yeah. Those people. Alright, so once we learn how to find the magnitude of a vector, you're going to see that coming up with these distances, really not complicated at all. Alright, we could even figure out angles that separate them, all without using the law of cosines. Alright. Very user-friendly stuff. Now, these are kind of fun examples. They don't really, I don't know if they lend themselves too much to a test or anything, but all you're doing is you're creating for A, you're creating a vector that's 3 times the length of the one that's given. So a little bit of measurement goes a long way. Vector addition and scalar multiples and things like that. This is the kind of problem that I prefer that you try to wrestle around with first before I do it all for you, because it's really tied together with this concept. All right, but it doesn't seem like it would be. But I want you to try to think about it a little bit on your own first before we dive into it together next class. Magnitude. Now, if we think of the magnitude of a vector as the length of the side, or the length of the vector itself, then a Pythagorean relationship should kind of like scream at you. You know, because when I drop this altitude here and called it 3, I have 2 legs of a right triangle, a leg of 2, a leg of 3. If I wanted to find the value of u, if u is the length of a side, then I would just use the Pythagorean theorem. All right, the notation can be a little funky though, because u is a vector. So a vector is not a scalar quantity. A magnitude is a scalar quantity. That's an actual distance. All right, so u could never be equal to, in this case it would be what, the square root of 13? It would never be u equals that. It would be double barred bracket around u equal to the square root of 13. So in terms of the notation, acceptable alternative, use the absolute value brackets. right? Because magnitude is really talking about the value of the vector. And it should be an absolute relationship because you're taking the square root of positive numbers, so it's going to be positive anyway. So they just usually use the double brackets to distinguish cases where you're using an ordinary absolute value function and you're using the vector magnitude approach, right? So how can we just use this? Well, they're interchangeable essentially as long as you don't get confused about which is which. That's the only reason why this exists, because people will get confused. Like if you're taking a magnitude of something that has an absolute value in it, then what's the, like what are you supposed to do there? The good news is we're hardly ever going to be dealing with strictly an absolute value function in this course, so we can just go with this notation, right? So I tend to go with the double when I'm doing it in class just because I feel cool doing it, but single absolute values are fine also.
When do you use when you put the arrow on top of the letter versus just having the letter there?
You're supposed to do that every single time you're denoting a vector. I'm never going to do it. I just can't do that.
Oh.
It sucks. Because it's like you go through a problem, and then now I got to go back and put a little arrow thing on top of every U. It like drains my life force out of me every time I have to do it. I had to do that when I was a student, and I promised myself I'd never make the students do it. So what I do is, at least in type form, I try, and you can see in many cases I failed, I try to use an italicized bold-faced letter, U or V, to represent a vector, because that's also an acceptable way of representing a vector. It's just, I also forget to do that too. So essentially, you're relying on this notation to tell you when it's not an actual vector. These are indicating that it's a magnitude. If you don't see those brackets around it, that's your indicator that you're probably dealing with a vector in component form, all right? Which are usually pretty easy to spot. Because generally they say things like, it's vector V, like in example A here. Find the magnitude, all right? So if I'm looking for the magnitude of V, it would be the square root of -6 squared plus -8 squared. Yeah, you're going to get a clean 10 out of that. So 5 times the magnitude of V, 5 times 10. All right. It's the third one, part C, where we're actually going to kind of discover a relationship. And it's pretty cool. So we're asked to find the magnitude of 5V. So let's figure out what 5V is first. It's a scalar operation. That's the same as 5 times -6, -8, which would be -30, -40. If I'm looking for the magnitude of 5V, I'm looking for the magnitude of -30, -40. And it's Pythagorean again. I mean, it's really just a Pythagorean theorem. So we're looking at 900 plus 1600. So actually, let me just write 2500, which gives us a 50. All right. So the relationship that we get from this is a scalar relationship or a scalar multiple associated with the vector magnitude. All right. So from this, we discover a rule, and that is that k times the magnitude of V is equal to the magnitude of kV, where k is a scalar.
All right. Now the terminology, I mean, it's a little bit of an adjustment in the early goings if you're not familiar with it. Vectors, we're starting to get a sense of what those are. The term scalar, we'll throw those in from time to time. All a scalar is, if you really want to oversimplify it, just to have a working definition, it's just a number. Just some kind of number that you're multiplying by.
Just the case.
Doesn't have direction.
Doesn't have direction, it's just a particular length or a multiplier, a constant multiple of a function. Right? So if in that case, it should be a little easier. So take the k and make it a 2 or 20, but you wouldn't make it another vector. Vector multiplication is something completely different. So if I'm multiplying two vectors, there's a couple of ways I can do it. We could do it with something called a dot product, or we could do it with another approach known as the cross product, something that we'll talk about next time. Look at the wrong vectors. So m plus p is really just telling us to take the corresponding parts of vector m, which is 5, -7, and -1, 3. So the 5 gets added with the -1 to give you a 4. The -7 gets added with the 3 to give you a -4. And the result is a brand new vector which represents the sum of the two vectors. All right. So yeah, Calc 3 is not bad. Just adding stuff. The second one, which I'll have to revise my answer key later on, but it's really some scalar multiples and doing the same stuff. So what I like to do, ideally correctly, is do the scalar multiples on the fly. So double the m vector, making it 10, -14. Triple the n vector, making it 0, 12. And then, so this one, this is a fun little one there. All right, so minus vector p, we don't really call it vector subtraction. It's vector addition if you're just adding a negative vector. So in this case, what I would do is I would add the negation of p, right? So to keep it with straight sums. The reason why we would do that, or at least get in the habit of doing that, is based on the graphical representation. It's easier to see the result of vector addition because it's really just this. You're finding the diagonal of your parallelogram. That's what vector addition is. Vector subtraction, what is that? Well, it's still finding the diagonal of the parallelogram. It's just one of the vectors is going in the opposite direction from what you would think it is. So in this case, if I were saying minus p, I'm talking about the negation of this vector, right? So it would be going in the opposite direction of -1, 3, right? Also, it's a little easier to do the math, I guess. A little bit. So 10 plus 1 is 11. Fun fact of the day. -14 plus 12 is -2, minus 3 is -5. And you'll see some instances later on, especially when we get to 3D, where a negative, or like a subtraction of a vector, is better served as a addition of a negative vector. All right, visually, it'll become painfully clear. All right, next one. Get rid of that. I'm going to try to get fancy here. Unfortunately, I can't see through my own hand yet. That's as close as I'm going to get. All right, so I think that doesn't make any sense. I don't want the whole thing, for crying out loud. All right, pause.
All right, let me just do this as a recording. The whole world should see how terrible this is becoming. All right.
And now, line up to the W that's in the page. So you don't have to duplicate it a third time.
Oh, yeah, it's a good call. Good call. Meh. And meh.
There you go.
That's that.
You got A now.
All right, we got A in the books. All right. I needed a win. We got a win. So this is A. All right.
Beautiful.
All right. Nice. Nice. All right, now B. B's the fun one. I like B.
Just borrow one of those.
Yeah. Oh, well.
That's what you have to do.
Oh, you can just duplicate.
Yeah, I'm just going to duplicate.
Oh, you duplicate.
I duplicated everything. I overduped.
So you duplicated only one arrow though.
You might need a couple others.
Well, I need V plus W, so I got my W.
Okay.
You just draw a line between the original one.
So I got a V over here. I just had a V hanging out there. So here's my W, and here's my V. Now this,
Does it matter which one comes first?
no, that's the good news. Because the tail to tip approach does not require one to go before the other.
Okay.
Right? So I'm going to just freehand this one because you've seen what happens.
It's going great.
Yeah, I know. It's like, it's a work of art is really what we're looking at here. Actually, I don't need the arrows on this. And then,
Just go straight across.
yeah, but I want to make it look all nice like.
Oh, okay.
And then, and so this is V plus W, or W plus V, because the good news is with vector addition, it's commutative. It's commutative both visually and through the operation. So,
Wait, wouldn't have V plus W just been the line lined up with the other V? Or does it have to be like the angles?
It has to follow.
it's got to, wherever you start your journey, your V plus W is going to start there, and it's going to end after the journey is complete. So, it's kind of like,
It won't just be W being a straight line.
it would not.
Okay.
It would not.
You have to do
Because the angle relationships have to be held on to.
Oh, okay.
So I always looked at vector addition as like you have, two different people taking two different routes to a location.
The result of those two routes.
Yeah,
It's like statics.
yeah.
Like everything else.
I always look at it like they're like, oh, I'm gonna make a right at this place, and then make a left there, and I'm gonna do that. And I'm like, well, I'm just gonna like cross the street, and I'll be there. Like, so I'll just do that because that's pretty much what it is. All right. So then the 2V minus W. All right. So this is already entertaining. So 2V plus negative W. All right. So this one's a disaster waiting to happen because I am ungroup. Yeah, the rotate. So I think I'm definitely freehanding because it's.
Or you don't have to rotate. You just draw the arrow pointing somewhere else.
Yeah, just the opposite direction. So here's my negative W, with every intention of being the same length as W, and also at the same angle, even though it's not.
Just put drawing
It's
the scale.
Close enough. See, it's grouping everything. I don't want anything grouped. This I can move up. All right, so that we have one V and we have another V. All right, so that's our 2V. All right, again, it's commutative, so you can go in either order. So here's my start. I opted to go with the negative V first. All right, I could have done the 2V first if I wanted to. If neglecting the entire parallelogram approach, I could just go start to finish in one shot and have my vector sum. So 2V minus W. Now, if I wanted to draw the whole shebang, it would be something like this. All right, without all the histrionics, of course. One day I'll learn what the word histrionics means. I'll get rid of that because it served no purpose. All right, so a very important concept to understand the visual implications of some of these things, because when we get into derivatives involving vectors, it sometimes can be like very rote and procedural, where people just like, okay, I'm going to take the derivative, and you really have no idea what it means. It isn't until you get a sense of spatial relationships that you really start to get a good handle on it. That's like kind of secondary. More primary to that is what's going to happen on the test is I'm going to give you a problem that's got different rays like this, different vectors, and I'm going to tell you to find the graphical result of a vector operation. And what I tend to do is also give numbers. It's sort of a trick. It's not designed to be a trick question. It evolved into a trick question. All right? It's really to sort of separate the people who actually understand what's going on and the folks who are just following steps. So what I'll do is I'll say vector v is 2, 1. Vector w is whatever. It doesn't matter what they are. And then I'll say find all these things graphically. What that means is you're using an approach like this. Now, you can go, you could be as artistic with it as I am, which is to say that you could do a lot of freehanding as long as it looks good, but it still needs to be a graphical approach. So if you were to do so, if I told you vector w was 2, 2, and you just wrote the answer is 6, 6, why? Because I multiplied stuff. But I asked you to do it graphically, you're not going to get any credit for that, right? And I have this argument with people every semester, and I really shouldn't, because if the directions say graphically, but I got the right answer, and they're like, yeah, lots of people get the right answer. 2 is a very common answer, believe it or not, on math tests. Just the number 2. Odds are, on a test, if you write the number 2 as an answer to like every single question, odds are you're going to get one of them right, because it's probably the answer to something. So yeah, just because you got the answer doesn't really tell me anything. All right. I was going over linearization in my calculus class, which is basically using a tangent line to come up with an approximation. If you don't know what it is, come up with an approximation for like roots, the cube roots, or whatever. So you're supposed to use calculus, derivatives, substitutions, things like that. So I gave a test. The student turned in the test. The question asked for the cube root of 60. They gave me the cube root of 60. They typed in the cube root of 60 in their calculator and wrote the answer down. I'm like, that's wonderful. However, I needed you, because it said in the directions, use the method of linearization to determine the cube root of 60. I was like, but I got the answer. No, okay, technically, but you didn't do any calculus. So that's an issue. So the directions are important. If a question says to do it analytically, you do it analytically. If it doesn't say anything, do it any way you want, short of cheating. If it says to do it graphically, you have to give me a graphical solution. All right. The numbers, I hardly even look at the numbers. I look at the picture. If the picture's right, you got the credit. If the picture is wrong, that's when we start looking at it for deductions. All right. So hopefully this little spiel is going to kind of stave that off. Hopefully. That's the plan. That's my... So there's some more properties here. And I'm just going to put a star on this example here, because I think, I know, it's the kind of example where I've gone over it before in classes, and it's not, it doesn't land. It doesn't land unless the students have considered the problem first. Like, I'll go through it and you'll be like, oh, cool, congratulations, you can solve a problem. Like, no, I need you to solve the problem. So
try it on your own first. Do it on separate paper if you don't like destroying your notes. But this is something that's important. So we're going to talk about that in next class. But before we go, the very last concept, which will only take a couple minutes. I know we're all looking at the clock. And again, I'm not going to always keep us so late. It's just in this time of year, because I don't know how snow is going to impact things. I got burned big time last year. Like this topic, we didn't get to until like mid-March because of all the snow. We lost like four classes due to snow, and then I was sick one time. So it was a disaster. So, I mean, maybe not from the student standpoint. They were like, oh, cool, half the course.
Nah, that was miserable. It was like I had Calc 1 a year ago when that was happening. And Professor Simpson was like, nah, like I live up north. So I even had even worse.
So you had to, yeah.
I missed like half the semester. And then he still quizzed me on crap that I didn't even come in class to learn yet.
Yeah. I mean, it's tough. So I figure if we could just kind of hit it hard early on, later on when the weather is more stable, then we'll see where we're at. Right, so it's like, man, this guy sucks. He's going to keep us here at 8 o'clock every night. Like, I might still suck. It just has nothing to do with that. Right, so, component form of a vector using trig. Right, it's all coming back to the trig. It will always come back to trig. So, I'm designating the hypotenuse of this triangle as 1. I'm doing that for a very particular reason, because this triangle is a subset of the unit circle. All right. And the horizontal distance in the unit circle, x, is defined as cosine of theta. The vertical distance, y, is defined as the sine of theta. It's like magic. That's so great. So, if I'm just focusing on the lengths being cosine and sine respectively, what we have is a transition from one triangle to another. It's just scaled up. These two triangles would be in proportion if I bothered making them not identical looking triangles. But what would happen is, in order to get from a 1 to a v, a magnitude of v, I have to multiply by the magnitude of v. So I'm going to do that across the board. So my horizontal distance would be the magnitude of v times the cosine of theta. My vertical distance would be the magnitude of v times the sine of theta. Which begs the question of why I bothered underlining it in blue if I didn't write it in blue. Yeah, and I can't even erase it now. Yeah, well, whatever. I had every intention of color coding it, so that's got to count for something.
Fault was there.
Yeah, it's the thought that matters. So, the magnitude of v is the length of your hypotenuse. But what we have now is a way of figuring out the length of your components based off of that information. All right? That was louder than I intended. So the component form of a vector using magnitudes, we would say, let me just chuck it here, v cosine theta, comma, v sine theta. All right. Now that scalar rule that we talked about just on the previous page, I think, I did that for a reason. It's to introduce this particular idea. I can factor that out. And get the magnitude of v multiplied by the sine of theta, comma cosine theta, comma sine of theta. Right? So that's an important concept. If we're looking for the component form of a vector,
it's an important concept because we're not always going to be given particular dimensions. Sometimes we'll be given an angle, right? So they're telling us that the magnitude is 4. All right, so they're telling us V. And then they're telling us that the angle is negative 45. So that's our theta. So if I want the component form of this vector, it would be 4 multiplied by the cosine of negative 45, comma, the sine of negative 45. Unit circle trig, right? And I hope it's clear in this that I'm not forcing this to happen. Like, this is the natural progression. This is what naturally happens. The Calc 3 makes an awful lot of use of the unit circle. All right, so I'm not inventing problems just to justify the fact that I told you to learn the unit circle. I promise you, it comes up over and over again. So if you haven't made it your business to become familiar with this unit circle, you got to do it. There's an expiration date on this. You're going to get to that point because you're looking at cosine negative 45. Yeah, the calculator can help you out, but if this is a small part of a really lengthy problem, it really helps if you have that information at your fingertips. I mean, at the edge of your brain. So negative 45 is fourth quadrant reference angle. So radical 2 over 2, negative radical 2 over 2. And then I could run through with the 4. I mean, I could have left the 4 inside to begin with if I wanted to. But the component form of this vector would be 2 radical 2, comma, negative 2 radical 2. Because again, you know, it was the joke before, but like, I am not asking you to come in with protractors and compasses. Okay? So if I told you that you had a magnitude of 4 and an angle of negative 45 degrees, and you had to come up with a component form, you're either doing one of two things. You're either converting from polar form into rectangular form, which is essentially what just happened here, which involves unit circle, or you're going to try to sketch this out, which involves estimation, and I don't know how you're coming up with an exact answer if you're estimating the whole way. Right? So you could probably finagle some right triangle trig to get the job done, but it does help if you know these facts. That's what I was talking about before, about this being a fact-based course. You know this information, you're good. If you don't, the opposite of that. All right? So I say this all the time. This stuff, if it looks like black magic, like, where did this stuff come from? I'm talking to you. Go home, study the unit circle. If it looks perfectly fine and familiar, then you're probably not having any trouble with anything that I'm saying, aside from when I screw up a problem.
For Calc 1 and Calc 2, our teachers are usually used when we have like pi divided by 12. Are we going to use that a lot in this
No,
course?
no.
As long as I have the other 3.
Yeah, the other 3. Yeah, the only time pi over 12 is coming into play is if I ask you to graph something, but then I'll give you the graph that has pi over 12 on it.
Okay. I'm good.
The subject tune.
So graphically, as an example, you would want that drawn.
Yeah. Yep, exactly. All right, this is the problem that I said I wanted you to kind of chew on first before I went over it. It's actually not that crazy, but there's something that needs to be done, you know? So let's clean it up. Oh, that's me cleaning it up, by the way. Let U and V be 2 non-zero vectors that are non-equivalent. All right, so 2 unequal vectors, basically, assuming they're not 0. Consider the vectors A equals 4u plus 5v. So I'll just make a note of that.
Did you stop it being paused?
I did. and b is equal to u plus 2v. They're both defined in terms of u and b. All right. So we have vectors a and b that are defined in terms of u and v, which are other vectors. So vectors defined in terms of other vectors. So it's a weird thing to think about. We have a plus lambda b.
Plus what?
Lambda. It's that upside down funky y. All right. That's going to be equivalent to u minus v. All right, so all we need to do is figure out what lambda would be, the scalar lambda. It's just basically a multiplier. There's something that we're going to learn about later on in the course called Lagrange Multipliers. Also uses lambda. Lambda is a typical way of representing a scalar. So we get into some Greek letters. Sometimes it's just the way it works. All right. So, but it will be defined as either a scalar or a vector. It's not going to be left open to guessing. So don't be alarmed by it because, okay, it's called lambda, whatever. It's just like a k. Right? It doesn't matter. So why not use a k? Well, yeah, I know. Anyway, these are going to be equivalent. So all we have to do is figure out what lambda would allow that to happen. So it's just substitution. So I'm going to do 4u plus 5v. That's going to take care of the a, plus lambda, poor quality lambda, u plus 2v. And that's going to be equal to u minus v. Okay, so, little housekeeping. 4u plus 5v plus lambda, poor quality lambda, extra poor quality lambda, terrible quality lambda, lambda u plus 2v lambda, really doesn't matter what order you put it in, all right, so 4u plus 5v plus lambda u plus 2v lambda, or 2 lambda v, equals u minus v. All right, so what we want to do is really just collect all our u's, because 4u plus lambda u should be equal to just a u. All right, it's kind of like, well, actually, I don't know if this is an analogy that's going to land, because I teach partial fractions slightly different from the way other people do. So maybe this will make no sense to you, but this kind of works the way, if you had me for Calc 2, the way we did partial fraction decomposition. It's just we had a variable u. We were just trying to make a determination of what the coefficients would have to be in order for the left side's coefficients to boil down to equal the right-hand sides. In which case, there really isn't much to do, because all I'm saying here is if I have 4u, I mean, I could do some factoring and stuff like that, but if it's 4 plus something equals 1, I'd just be asking really what is the something? -3? Yes, indeed it is. Because 4 minus 3 does in fact equal 1. All right, so then just for giggles, I'll make sure that that works for the v's. I have 5v plus 2v v lambda equals, I'll write it as -1v. And so the question would be, if I replace the lambda here with a -3, does this one also check out? Because if it works here and fails there, all bets are off. All right, so this would become 5v minus 6v would give us a -1v. All right, so we have successfully found our scalar lambda to allow one side to equal the other. All right, this is a little taste of what's to come, because we're going to expand upon this idea in a different way, definitely, but with a concept called Lagrange multipliers. It deals with optimization in 3 variables. It's really cool stuff.
Did we have to
Yeah, I mean, you could, the vector operations work pretty much the same way, so, as the algebraic operations. It's only within a vector that things get a little dicey, but as a coefficient to a vector, you could still play it out the same way. All right. The only time things get a little hairy when you're dealing with vectors is when you're multiplying a vector by another vector, like actively multiplying them, right? Because that's when you get into dot product and cross product, which we're going to get to. But here we're only really multiplying by scalars. Scalars they act as constant multiples.
I was wondering, because now that you mentioned that, if you subtracted the 4u plus 5v, and then afterwards divided the u plus 2v, is that something you're not allowed to do only because it's vectors? Because I still got the same answer, but I was wondering if afterwards, everything that's right next to lambda, if you divided that out to get the same answer, would there be something wrong with the dot product? Like
No,
what you were
no, it would still work because we're only,
still scalar?
yeah, because we're still in scalar land right now. If this were something like, instead of 4u, if it was like uv, then it's a different story, yeah.
Because it's a vector divided by a completely different vector.
Correct. That's when all hell breaks loose. But that's all right. We'll cross that bridge. All right. Number 2, find a component form of vector v with magnitude 10 that forms an angle of 120 degrees with the x-axis. All right. So all the ingredients are there. So we have the magnitude, and we have the particular angle. So we're looking at 10 cosine 120, comma 10 times the sine of 120. So as long as you know, I can't make the star go away. It's going to make it seem like this is the most important problem on the page, and it's not. All right, hold on. I gotta white it out. I had that happen before, where a student bombed a test and afterwards told me that they only studied the questions that had stars on them. I'm like, no, those are the ones I was just asking you to do for homework. Like, that doesn't mean they were any more important than the others. So, yeah. But I guess it's a good thing to talk about. So yeah, in order to find the component form, knowing the magnitude of something other than 1, you just simply multiply the vector by whatever the magnitude is. So it's just a question of, do you know your unit circle?
Cosine of 120 is
Negative
1/2.
1/2.
And the sine of 120 is radical 3/2.
It sure is.
And so that's negative 5 radical 3.
And 5 radical 3.
I still have to look at my phone for that.
Boom shakalaka. In a little while, I'll talk to you about a bonus opportunity that will hopefully motivate you to really get to know this unit circle. And if you already know the unit circle, you should be able to burn through the bonus opportunity pretty easily. But I'll talk more about that later. Yeah, you know, it's funny. Like, people, like, if I tell you, know this unit circle and you'll do really well on the next test, it's like, oh, okay. Know the unit circle and you'll get 2 bonus points. Like, oh my God, how do I do this? 2 bonus points, let's go. And I'm like, yeah, but if you do really well on a test, that's like 40 points. Like, the 60 is like 100 now. Like, what? I don't know. It's the idea of bonus. It's like, it makes people go crazy. You know, like, what was that movie reference?
Dark Knight.
Very good. So, unit vector, the vector with magnitude of 1. So that's easy enough. A unit circle is a circle with a radius of 1. So a unit vector is a vector with a magnitude of 1. All right, for any non-zero vector v, we can use scalar multiplication to find a unit vector u that is the same direction as v. All right. We talk about this a little bit in linear algebra, but it's the idea of the basis of a system. Is that if you know what everything scales down to in a single unit, then you could define a whole system based off of that unit. All right. So it's kind of like the rectangular coordinate system. You define each movement on the x-axis as one unit, so that anybody could interpret what you were saying. If I said that I'm at location 10 on the x-axis, you know that that's 10 1 units, right? So if I find a unit vector that's going off in a particular direction, then that defines the language of that vector. So if I'm off at magnitude 30, I can redefine the length of that vector in terms of the unit vector, right? So everything would be a multiplier of that unit. And so we can actually reorganize an entire coordinate system based on our knowledge of a unit vector. That's how important this concept is. In terms of how to do it, well, it's that. 1 over the magnitude of v times v. Or, most people like it this way. Kind of cuts down on the fluff. And again, just to refresh, we said that we could write it as just an absolute value. In terms of the notation, these two are considered to be interchangeable. All right, so we have our basic unit vectors, the ones that define our Cartesian plane, our rectangular coordinate system, I and j. So I is the vector 1, 0. J is the vector 0, 1. Every number in the coordinate system can be defined based off of these two vectors.
Would you have to use hat notation, or is it
Nah, you just write it without it.
really stressing notation with
What?
last class?
Yeah, it's notation. There's a time and a place for it. I just personally, if I forget to do it, I'm not gonna make you do it. And also, I just pretend that I made it bold, because that's the other alternate approach. I mentioned this last class, that you could do it with a little jammy on the top, or you could write it in bold font, like bold I is vector I. Regular font I is just I, like maybe the imaginary unit I. Right? So I look at that and say, yeah, I totally meant to make that bold. It's bold, just pretend. Right? So that's what you'll do too. Right? And really, if you understand the concepts behind it, you know when something is a vector and when something's a scalar anyway. All right, so no real emphasis on that idea. But we will have some notation considerations that we'll have to take into account, but it's not this. So anyway, if, for example, I had, I don't know, 5, 4. Probably stealing my own example. You can even think about it in terms of coordinates. 5, 4, it can be thought of as 5 1 zeros and 4 of the 0 1s. Now, if I'm telling you that 1, 0 is the same as I, then it really becomes 5 I plus 4 J. All right, so you kind of cut out a little bit of the fluff there and say, all right, so what you're saying is take the X component, slap an I on it, take the Y component, slap a J on it, pop a little plus sign in between those two bad boys, and you're good to go. All right, yeah, and that's true. All right, that's the relationship that's there. All right, but then the question becomes, all right, well, we have these unit vectors that we can work off. What if I want to redefine my system to be in terms of a brand new unit vector, something that maybe is not perpendicular, or maybe not involving an axis at all, maybe something going off into space? All right, so maybe I have vector v. Just throw an example here. Call vector v 2, 3. So I could put that in IJ notation, sure. But what if I want to find the unit vector? Unit vector U would be V over the magnitude of V. So on the top, it's actually the vector itself. On the bottom, we'd have to figure out what the magnitude of V is. Sum of the squares. So the square root of 13, exactly. All right, so it's Pythagorean. All right, I'll just jot it off on the side. It's the square root of 2 squared plus 3 squared. All right, so two components squared and added together. Basically the same formula as finding the R value to convert from rectangular to polar form. All right. Now I can clean it up further and make my new unit vector 2 radical 13 and 3 radical 13. 3 over radical 13. 2 over radical 13, 3 over radical 13. All right. So what that gives us is a vector whose magnitude is equal to 1, but that vector goes in the same direction as 2, 3. So if I were to draw, I'll just draw an insanely rough sketch of this. This is 2, 3. And that's V specifically, but the unit vector would be something like this. That little guy I just drew there. That would be U. All right, so the benefit of doing that is that, again, we could redefine our system in terms of this new unit vector. All right, anytime you can think of a situation where you need to do a unit conversion from one form to another, this idea comes into play. All right, I mean, it's something simple like the metric system and the standard units. You know, so you want to go to inches to meters, or miles to kilometers, or whatever it is. You know, you're doing a unit conversion. If you don't know what one unit is equivalent to in the other system, then how do you do your conversion? I mean, we did it earlier. I mean, at least at some point, maybe not literally us, but at some point you did when you convert radians to degrees. You know that 1 degree is equal to so many radians. You know that 1 radian is equal to so many degrees. You know, if you don't know what the base units are, the basis of the system, then you can't make a conversion, right? And so this kind of leads us down that road. All right. So the examples that follow are pretty straightforward, I think, when you take it in that perspective. Numbers 1 and 2 are just, I mean, they're not even really questions. Negative 2i plus 4j. 0i minus 9j, so negative 9j. The third one, vector u is a unit vector that forms an angle of 60 degrees with the positive x-axis. Use standard unit vectors to describe u. All right, so standard unit vectors, that's ij. All right, unit vectors are defined based off of a particular vector that you're given. That was the side example I did before. All right, so if I'm talking about an angle that's 60 degrees with a positive x-axis and it's a unit vector, what is that vector going to be?
1/2 I plus radical 3 over 2j.
Right, so 1/2 radical 3 over 2, and then when we use standard unit vectors, we're going to put the I and j stuff on. Now, of course, you were dying to do some word problems, specifically involving wind blowing and planes and things like that. Possibly a person trying to get across a lake. Maybe a hot air balloon question will work its way into our adventures. All the classic calculus questions. You know the cut the corners out of the box, the cardboard, and flip it up, make a box out of it. Has no top. Yeah, we got one of those in this course too. Like every course, we got one of those. We always save room for one of those bad boys. So here it's actually a very basic problem. Jets flying at a velocity of 500 miles per hour due north. All right, so start off with that. I'm going to identify due north the way a normal person would. All right, I'll call that vector n. Now, vector n has a magnitude of 500. All right. It encounters a wind blowing out to the west at 50 miles per hour. So west, again, the way a normal person would. The magnitude of vector w is going to be, well, west is to the left, and right and up are positive vectors, left and down are negative, so this is going to be negative 50. All right, you can include the units now or later, but at some point they're going to be there. Draw a diagram and use it to find the jet's resultant velocity to the nearest tenth. All right, so instinct is something that you probably want to fight here, because we didn't just spend all this time learning about vectors to draw a hypotenuse and use the Pythagorean theorem. All right, so we might have a little bit of an issue when it comes to that. So what we would want to do, we have our magnitudes, that's all wonderful.
Units alongside though, like it's going 500 miles
Yeah.
per hour, and you have the exact same thing you just had, but now it has a unit that says, by the way, there's a time component to all of this somewhere in the cosmos.
So yeah, like n is equal to 500t and w is equal to negative 50t. You can't do something like that.
Now we're doing physics.
So the vector would be defined by cosine theta, sine theta, you know. Right, but this is the part that's going to make it work, so that's...
If we left it the way you left it, would we get that wrong?
Depends on where you went with it, because it wasn't going to end well the way I was doing it, so that's why we're doing it this way. So vector n is defined by cosine theta, well, every vector is defined by cosine theta comma sine theta. So cosine 90 sine of 90, and that would give you 0, 1. All right, so that's it. That's our unit vector, and that's the way it's going to play out. We will need the sum of the unit vectors in a minute, but the w cosine 180 sine of 180 negative 1 0. All right. So if the magnitude is something other than 1, we're talking about a unit vector here. If the magnitude is something other than 1, what we do is we tuck in whatever the magnitudes are. In this case, for n, it's 500.
And then you have to change what you put in for w. W is supposed to be 50 because it's a magnitude. You
Right, yeah, so that the direction doesn't matter anymore because it's already accounted for in the vector. All right, so then we would multiply each of these by the respective magnitudes, in which case I would be looking at 0, 500, and negative 50, 0. All right, so that's the justification for why it works the way it does. Now, what we want to do with our diagram, the diagram was fine, it's just all the other stuff was the problem. So, still the tail of the tip. The reason why I would do this is because we're looking for the sum of the two vectors. All right, so if we're looking for the sum of the two vectors, I'm looking to add 0, 500, and negative 50, 0. And this is what I was talking about before, where it's like, we're not simply doing the Pythagorean theorem, but we are kind of, because it works its way into the solution of the problem, because when you find a magnitude of a vector, that's in fact what you are doing.
So in the problem, there was never like anything stating that, make use of the unit vector. Do you feel like during the test you would state something like that, like make use of the unit vector? And then
I would tell you specifically the way I wanted you to do it, yeah.
So like, from the way it's phrased now, what you were putting down before was a perfectly fine answer, without having to actually write down, okay, cosine of -3 is
Right.
the way it's phrased now.
The way it's phrased, it's just I need to gear you up for the way it will be phrased, you know.
The way it's phrased now would have been fine to just use the
Pythagorean. Yeah, you just draw a triangle, a squared plus b squared equals c squared. So, yeah, that part of it is what it is. So, we find the sum of the vectors, but then we need the magnitude. And you could define that vector any way you want. I mean, you could call it S for sum.
It worked its way in.
It always does. So the magnitude of S would be equal to the square root of negative 50 squared plus 500 squared.
502.5.
Approximately 502.5. And does it seem unnecessarily complicated? Yes, of course. Am I going to give you a simple case on a test where it's just north and west,
No.
where you could use a Pythagorean? Of course not,
Two
because
different
You
angles.
just
Yeah.
sum them up anyway and use Pythagorean.
Yeah.
You never need the unit.
well, that's the
For this
thing.
one.
I mean, like, do you really? Of course not.
I mean,
But to justify
If
it,
there's different angles, you can still figure it out even without having to use this stuff because you can break it in your x and y components.
exactly.
Somebody might draw
But the good thing about when you're given the angles, when you come up with the appropriate vectors, it really is just a matter of adding them up and then taking the magnitude of the results. So even cases where you're dealing with funky angles, it's still the same approach. In fact, it was a blimp. Sorry, it was not a hot air balloon. My bad.
Change the whole problem.
Yeah, I mean, it was like you're looking forward to a hot air balloon. Now it's a blimp. It's like, jeez. But we do have a lake. Lakes are good. All right, so for a man to cross a lake to a point directly east of his cabin, which I suppose we're to assume is on the edge of the lake, he must set a course 6 degrees south of due east so as to compensate for a current that flows to the northeast, 30 degrees north of due east. All right, so that's fun. If the man's boat travels 20 miles an hour in still water, so if there were no current whatsoever, that's how fast it would go. What is the rate of the current to the nearest integer? What is the resultant velocity of the boat? All right.
Why does he want to put south of the
I don't know. This he's all messed up. So he's starting off at his cabin. He wants to get to a spot directly east of where he is. Right, east of his cabin. Here's a point directly east of his cabin. That's where he wants to go. So this should be the resultant. All right, all the forces at work here, this is the path that he should end up on. All right, he sets a course 6 degrees south of due east. So he's like something like that. But then there's a current that's going 30 degrees north of due east. So it's going meh. So we got 30 degrees and 6 degrees south, but I'm going to make that a negative 6 degrees because if we're assuming the resultant is going in the 0 degree direction, that's 6 degrees clockwise, so making it a negative angle. All right. The man's boat travels 20 miles an hour in still water. All right. So the magnitude of his boat, and I'm going to call this vector B for boat, the magnitude of B is 20. All right, because that's the amount of propulsion the boat is offering. All right, whether it will actually amount to 20 miles an hour is a different story, but he's applying 20 miles an hour worth of force. All right, so that's what's going on there. Now, we need to know the rate of the current. We'll call that vector C for current. And C, the magnitude of it is completely unknown. All right, so we'll have to figure that out. And then we also need to know the resultant vector. All right. So we need some vectors. We need some information here. First thing we could figure out is that we have 20, if we're dealing with a boat, and we want to just kind of cut to the chase a little bit. For the boat, it's 20 multiplied by the direction vector, all right, which is negative 6 degrees. So cosine of negative 6 degrees, comma, the sine of negative 6 degrees. All right. Without the 20, we're talking unit vector, but by multiplying by its magnitude, we're scaling it up to also account for the speed of the boat, right? Or at least the speed that the boat is contributing to this whole fiasco. That looks like a K. That's C with an absolute value around it. Anyway, for the current, we don't know that information, except we do know the vector, but we don't know the magnitude of it. That's what we're looking for. So I would say C multiplied by the cosine of 30, comma, the sine of 30. And we can figure all that out in a minute. All right, those are unit circle values. But you look at this problem and you say, well, negative 6 is clearly not a unit circle value. 30, even though it is, I mean, obviously we're going to decimal form at some point here, nearest integer. So even though they're unit circle numbers, you're going to kick over a calculator at some point. So whether you want to do it now or later is up to you. All right, the resultant would be the sum of these two things. All right, so you could do the distributive property and get things going, or we can at least evaluate the resultant component and then see what's going on there, because you just make a little note for the result. I'll just say equals. I don't know what the resultant is. We'll call it R. But I do know that it's going to be the result of cosine 0 degrees, comma, sine of 0 degrees. So R, comma, 0. So for the boat, I really don't feel the need to go to decimal form just yet. I'll do it later. I can run through with the 20 and make it 20 cosine negative 6, 20 sine of negative 6. If you want to go coterminal on that, that's fine. It's just it's dangerous. It's easy to screw things up if you make it the positive counterpart to the negative 6. So I say leave it. The calculator can handle it either way. For this one, maybe you do want to get those unit circle numbers involved. In which case it's radical 3 over 2 times C. So C radical 3 over 2 and C over 2. All right. The sum of the two vectors, I can illustrate it here a little bit. Poorly, of course. I don't want you to get spoiled. Yeah, look at that parallelogram. That's disgusting.
Not drawn to scale.
Just
not drawn to scale. So if we add our components together, the result should be the resultant. So 20 cosine negative 6. So we're essentially going to get a system of equations here. So 20 cosine negative 6. I'm going to go blue for those keeping score at home. 20 cosine negative 6 degrees plus c radical 3 over 2 should be equal to r. All right, equation with two variables, that's fun. The other one's not as bad. We have 20 sine negative 6 degrees plus c over 2. And that's going to be equal to 0. The second one is where we earn our, well, not, I was going to say earn our keep, but not really because it's easy enough to do. I'll put parentheses around here because it's starting to look a little nasty. So we can solve for the value of r here with our calculators. I'm just going to crunch it out real quick. I don't think we need to actually see it. We're working with degrees, so you'd have to be in degree mode. Oh, actually, you know what? Let me show you that real quick. So you don't have to change your mode on the calculator. I only learned about this when I became a teacher. And so we generally want to live in radian mode, but every now and then we have to do stuff in degrees. But I don't want to change it to degree mode just for like one or two problems because I'm going to forget to change it back and then screw up every problem after that. Right? So what I do is I leave it in radian mode. And when I need to figure out something like 20 times the sine of negative 6, I'll type in 20 sine of negative 6, but I'm going to put a degree symbol in. All right? The degree symbol you get by hitting second. See that angle menu right above apps? It's the one for converting polar to rectangular coordinates, same menu. So second, apps, pull up that degree symbol, and it'll treat whatever precedes it as a degree rather than a radian.
So you don't have to go back and forth.
Exactly.
Yeah, in your next class and then fail test.
Exactly. So that's what it should be equal to, in theory.
It is.
Nice. So then I'm going to add that to both sides and double it. So times, no, just do negative 2. So our R value is about 4.2. Sorry, C value. And then after that, it's plugging and chugging. So I'd plug in the 4.2 for C in the second equation. 20 cosine negative 6 degrees. So second apps, option 1, plus use my nifty fraction tool here, alpha y equals n over d. I'll take, so I want this answer. So I just hit the up arrow, hit enter on it, and it'll pop it right in there. Because I want to at least have some degree of accuracy here.
How'd you get the like division sign with the two sides?
It's fun, right? Let me do it again. So, although I wish I didn't delete the cosine part because I didn't need to do that. So second half 0. So plus, so alpha, y equals, and you have the fraction menu. The first one is numerator over denominator. Select that. It's glorious. Then I just want to insert the previous answer. So I'm going to hit up arrow, hit enter. So I'll just pop that right in there.
Awesome.
Times root 3. Hit the down arrow to get to the denominator, pop in a 2. Hit enter. And about 23.5. All right, and so these are speeds, miles per hour. All right, and none of these angles were right angles. So you're looking at something where, you know, we were able to do it linear equations and some knowledge of trig. You know, and I'm not even talking about like advanced knowledge of trig, the basic stuff. SOHCAHTOA. we were able to figure out this stuff. So no law of sines, no law of cosines, sum of vectors, set up a couple of vector equations. There are some problems where I will show you the linear algebra approach. So row reduction techniques, matrix operations, so it's really all in the calculator, because I also don't want us to get bogged down with the algebra. I'm just debating of whether or not this is the opportunity to show it to you. Nah, one fancy calculator skill per night. How about that? GeoGebra? Yeah, next week we're going to talk about the first technology assignment, which is going to be a GeoGebra-based activity. And 3D, you start to really see the value of GeoGebra for that. Because there are some things where, like coordinates, once you get a sense of it, being able to plot them in 3D, it's not too bad. But when you see a function of two variables, which you've worked with before in calculus, in Calc 1, but the idea that it actually represents a figure in 3 space, it can be alarming. And unfortunately, the calculator doesn't really do much for you there. Right? So GeoGebra helps you to get a sense of what these things look like, so that when you go into a test, you're not blindsided by a function. That was the whole thing. It's like, I could go through all the motions when I was a student, but then when it came to actually really truly understanding, I don't think I ever really truly understood what was going on until all of this technology was invented, which was like after I was a student, which kind of sucked. But then again, Google didn't even really exist in its current form then, so I can't really complain too much. So the point, when you're plotting a coordinate in 3 dimensions, or 3 space as we call it, you have 3 components. You have an x-axis, a y-axis, but you also have a z-axis. Right? So when you think about a 3-dimensional figure, there's length, width, and there's also height. Right? So this is incorporating potentially height if you're talking about linear distances, but it could be anything. Right? So at this point, we're just talking about plotting. This could actually be an Algebra 1 type of question, because it's really just like, all right, when you see this number, you move this way. When you see that number, you move that way. Right? It's as simple as that. All right. The first value in an ordered triple is the x value. Second value is the y value. And you guessed it, the z value. All right. So when you think of it that way, it's not too bad. But what you do is a little bit different, because we're graphing 3-dimensional objects on a 2-dimensional plane. Okay, it looks like it's a 3-dimensional plane, but the paper that you are writing on is a 2-dimensional plane. So everything is a perspective drawing. So we have to know the rules of the perspective, right? So if you think about the idea that what might seem like a rectangle, or like rectangular form, is actually a parallelogram, that tends to help. Right? Although, since I can't draw a parallelogram, that might be problematic. The x value is just the number of steps along the x-axis. The x-axis comes out of the page in your direction, right? So, well, perfectly in my direction, but maybe you have to kind of shift your body a little bit to really see. But if it's positive, it's coming towards you. If it's a negative x value, it's going away from you. You'll notice as you go through the packet, you'll see problems online. Nobody labels the negatives, all right? Because what happens is the graph gets too busy when you do that. So they only label the positives and then just ballpark the negatives. All right, so what I'm going to do is I'm just going to go out 1 unit in the x direction. This is not my coordinate. I'm just using it kind of as a placeholder. All right, so I'm just kind of like identifying that location. I should have done it in black. Color code, come on, man. Jeez, this guy. All right, so there's my x. Y is -2, so I'm going to go -2 units in the y direction. So positive y is to the right, negative y would be to the left. I need to go 2 units. So just getting a sense of what 2 looks like, I'm going to go 2 in the opposite direction. So there's 2. All right, so this is where the perspective comes into play. What I'm going to do is create a parallelogram using the sides connecting the points to the origin and the opposite sides. Just as you would if it were a vector kind of thing, like a resultant vector situation. All right, so this point here, that's actually 1, -2, 0. All right. If you're living in the z = 0 plane, you're in the ordinary Cartesian plane, x-y axis. That's Earth 1, right? That's the case where everything is as it always was. It isn't until you shift up in the z dimension that you're displacing out of the ordinary plane. So that's what we need to do here. We need to take 3 steps in the z direction. So what we do is we figure out what 3 steps looks like. Maybe use the side of an index card, piece of paper or something like that. Get a sense of what 3 steps looks like. And then just slide on over. Mark that off. And then plot the point in space. All right, so this is what 3 looks like. I am not going to successfully be able to do, yep, okay. It still is not something I'm capable of doing. That distance is what I need to have, but over here. So like right about meh. Maybe a little bit more meh. All right, so this point here is 1, -2, 3.
That's 2. No,
No, 1, -2.
it's this is the perspective of the.
Yeah, so it's going to look a little lower because it's been shifted downward, but it is going to be 3. Well, or at least the best I can draw.
Should be 3.
It's
Shifted back.
This distance.
Just write a D next to the line that goes 3, and then just
shift
just
it
put
towards us.
I see.
Just put,
Yeah, just label it with something.
just label it so.
I'll just do the old geometry labeling. Congruent. Nah, that fixed everything. It's great. Life. All right.
It's a scale.
And it's completely to scale. You know, it's a work of art. It looks better as I zoom out, of course. But yeah, that's how you plot a point. Now, you could already see how problematic it would be to plot an entire surface, which is made up of infinitely many points. How would you do that? How would you draw even a sphere in 3 dimensions? Right? It's not easily done. You know, there's like a lot of framework going into it, and really that's why I push GeoGebra a lot, because it does give you a true sense of what the images should look like without you having to like really destroy yourself trying to do it. When I took Calc 3, I'll tell you that I would say like half the course, or at least it felt like half the course, was just drawing this stuff. Maybe you would like that more. I don't know. Well, you wouldn't know that yet. But you know, some applications here. Write an equation of a plane passing through the point 3, 11, 7. That's parallel to the YZ plane. All right, so you got to start thinking about what these planes would boil down to. So if I'm going to just do a freehand on this, I have Y, I have X, and I have Z. So do it in any order you want, as long as you have them labeled properly. The XY plane, you could kind of think of that as the base, or the horizontal plane, right? That's the case where Z is equal to 0. Anything above or below that would be where Z is equal to 1, -1, -30, it doesn't matter. YZ would be this panel for any possible value of X. So it would be more of a vertical plane. And then the other possibility would be XZ, which would be this panel, which would be vertical but kind of the corner. So if you really want to get a true sense of what the X, Y, Z planes look like, it's right there. Right? So here's X, here's Y, and here's Z. All right? So XY plane, YZ plane, XZ plane.
Why don't we draw Z like what the direction y usually goes to on a 2D graph.
Well, because z typically, more often than not, represents the height of a figure. So it's really just trying to visually manifest that idea. And most of the time when we're dealing with x and y planes, we look at x versus y in the way that we do, because, well, first off, because somebody decided that that's the way we should do it, and that kind of stinks. I don't like it when that happens. But also, what we're really doing is just trying to kind of restrict our variables. So if you're defining something in terms of two variables, like a physical motion, odds are if the object's in flight, for example, the y-axis is going to represent the height of that object, whereas the x-axis might represent the the horizontal movement, but that's all along one plane, right? Because that's the thing. When you're dealing with those classic projectile motion problems, you know, like the thing thrown up in the air, find the max height, the ones that we all love, it's all on a single z plane, right? It's just your x, y, z plane has been juxtaposed, so basically flipped on its side, so it's really xz as your base with the y going up, just so that the textbooks and math teachers could take advantage of x versus y, with the implied aspect being that there is a z plane out there that would have some impact. But what happens is all those problems have the little caveat that the object's being thrown up in the air and then coming down. It's not wiggling throughout the approach. There's no curveballs, right? So the object goes in a straight line path. And I don't mean like the curve itself is straight line, but it's on a plane that is the straight line base, right? So it's shooting up in the air, but living on the same plane, as opposed to like a pitcher in baseball where they're not living in the same plane. They actually change their planes. The better pitchers do change their planes. So a curveball would start on a plane, then kick out into a different z plane, and then come back in, possibly going through many more planes. Right? So all of that stuff comes into play here, but you never could have done it before. Right? So really interesting stuff, and it's finally an opportunity for you to explore physical phenomena in a meaningful way, because it's like, yeah, I mean, I could throw stuff in the air, but to expect it to not have any lateral movement, that's unrealistic. Right? So when we're talking about writing the equation of a plane, though, that's not bad, because if it's parallel to the yz plane, you're just thinking about that. Here's yz. That means that it's living on some constant value of x. All right? So all we're really saying is that it's got to be on the x equals 3 plane. Because if it's living on some x plane, aka it's parallel to the yz plane, but it also has to go through the x value of 3, it must be on the plane x equals 3. Now, how could I define a plane x equals 3? That doesn't seem to make any sense. X equals 3 isn't that a vertical line? But x equals 3 in a two-dimensional system means x is 3 for all values of y. All right, so that allows it to be a vertical line. In 3 dimensions, x equals 3 for all values of y and for all values of z. So now it expanded to be the equation of a plane. All right, so it's little ideas like this, the transformation between two-dimensional systems and three-dimensional systems, which is where your mind needs to kind of take it. Now, I mean, there's rules here. You can read the rules. Rules are helpful, but the visual representation is where it's at. Go on GeoGebra, take some time, plot some points. There's a 3-dimensional calculator. Plot some points, type in some equations, see what's going on. It does pay off for you. All right, so that's where we're going to leave it, obviously, and we'll pick up.